the truth tables? Nobody noticed anything. These are all just random things. Like, what did you notice? Okay, wait, let me look. Who's got their homework out? Like number 11 and 12. I forget what it is. Too late. So you did a truth table for not P or Q. And then you did a truth table for not P and not Q. Okay, what did the truth table for this one come out to? Don't tell me! So false, 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 true. Did I do that correctly? Yeah. Of course, I'm the teacher. And then what about this one? False, 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 true? So what do you notice? They come out exactly the same. When two statements have exactly the same truth table, we say that the statements are logically equivalent. How do I know that? Because I looked at the notes. And what is the symbol that we use for logically equivalent? This. And doesn't that kind of remind you of an equal sign? Yeah. But see, only numbers can be equal. See, like the square root of 4 equals 2. But when you have statements, statements are not equal, they're logically equivalent. Just like numbers can be negative, but statements are negated. See, the symbols are similar. You know what I'm talking about? Okay, so what did we learn in last night's homework? The negation of the quantity P or Q is logically equivalent to not P and not Q. Oh, do we have to know that? Yes! Well, you don't have to know anything, you just going to have a hard time on the test, right? What else did we learn in last night's homework? What about the negation of P and Q? That's probably the next two problems, right? What did you find out about that one? That's logically equivalent to not P or not Q. Did you guys even notice that at all, or are you just doing the homework and just going to the next problem? See, the homework problems are there for you to learn. All the learning, well, not all, a lot of the learning is going to occur when you do the homework. Okay? Anyway, I'm going to box this. That's because it's important. These are called De Morgan's laws. Named, of course, after the logician Augustus De Morgan. Never heard? Could you even name 3 logicians? What's a logician? A person that studies logic. They dedicated their life to logic. Just like a magician, right? They dedicate their life to magic. Woo! Anyway, doesn't this remind you of a property we learned, like in algebra? Yeah, it's like the distributive property, yeah? So these rules allow you to distribute a negation sign to an OR statement or an AND statement. So you can distribute it, but then you have to change the OR to AND. And if you distribute it with an AND statement, then the AND changes to OR. Sometimes books call these the distributive laws. But real logicians know it as De Morgan's law. Okay, now what about the last 3 problems? What did we learn from that? Look at the last 2 problems. Look at 15 and 16. P or Q and R. P or Q and R. Okay, you did the truth table for that. Since there's no questions, I'm assuming you can do it. And then what was 16? Don't tell me. P or Q and P or R. You did the truth table for that. Hey, they came out the same. So what does that mean? These statements are logically equivalent. Not equal now. Logically equivalent. We don't have a name for these. But can you see it's kind of like a similar thing, yeah? Can you see the pattern? You're kind of distributing a P or to a Q and R. So you get P or Q and P or R. It's kind of like the distributive property, but not really. So you can probably guess that P, what if you had this? P and Q or R. What would you guess this is logically equivalent to? If you had to just guess, looking at the form. I don't know, Mr. Park, these are just random occurrences. No, they're not. Look at the pattern. P and Q or P and R. Can we assume this is true then? No! It has to be proven. Okay, so, on the next quiz, on Wednesday's quiz, Monday's quiz, what if I ask you, prove that this is logically equivalent to that? What are you going to do? You make a truth table for this, you make a truth table for that, and then you show that they are exactly the same. Then we can say that they're logically equivalent. We're just guessing this one you proved on your homework. This one, we're just guessing because the form is like the same, but no. We don't know for sure until you actually prove it. That's probably a good problem to put on a quiz, yeah. Probably see that one. Okay, so no other questions on the homework. What about the 1 through 10? Does everybody understand? Oh, no, okay. No, I just put the answer on it. Okay, so, okay, somebody read me the problem. Number 8. Some perfect numbers are odd. Okay, now, when you see the word sum, doesn't that mean like there exists? Sum means at least one, right, in mathematics. So this is an existential statement. Okay, and what did we learn? What's the negation of an existential statement? Universal. So how do I start a universal statement? Usually we say for all, but can't we just say all perfect numbers are. Now remember, how do you negate an existential statement? Look here, let's review from yesterday. There exists box such that triangle. How do you negate that? For all box, comma, not triangle. Right? So it's just this is like everyday language, yeah. But if you wanna put this in this form, you can, right? Like if you wanted to write this in this form, how would you do it? There exists a perfect number such that it's odd. Right? I mean, if you wanted to put it in this form. So if you want, that's fine. So if you want to negate it, then you would say, for all perfect numbers. Wait, that doesn't even make sense. I think it's just easier to do this. All perfect numbers are not triangle. So if triangle is odd, then what is not triangle? What's a better word than not odd? Even.
Oh, it's not the answer on the paper.
No, because it doesn't. No, I made the correction right there.
Oh, okay, sorry. Yeah, that's why I was confused.
Yeah.
Would it be wrong if you said it's not odd instead of saying it's even?
Okay, it's not odd, but that's like mathematically gauche. So that would have to take off a point. Bad form. It's just like saying x is not less than 2. Right? It's correct, but that's mathematically gauche. So you really want to say x is greater than or equal to 2, right? You know what I'm talking about, right? Okay, now, how do you determine if the original statement is true? Are any questions on those? Because those are the ones, okay, on the test, it's going to be 2 points each now. If you get the true, false part wrong, right? If there's 5 problems, that's why it's negative. First of all, do we even know what a perfect number is? So if you don't even know what a perfect number is, how can you even answer this question? 50-50 chance, okay? Okay, no questions. Anybody? You want to go over it? You want to discuss perfect numbers? Okay, what is a perfect number? If you don't even know what a perfect number is, how can you talk? Ah! Okay, a perfect number is a number where the sum of its proper divisors adds up to itself. Okay, the smallest perfect number we know of is 6. Now, what are the factors of 6? Or divisors. Divisors, factors, anything. What are the factors of 6? 1, 2, 3, and 6, right? Proper divisors means it doesn't include itself. Now, if I add up these numbers, it comes out to 6. That's why it's perfect. See, perfect. It adds up to itself. Did we talk about this already? Seems like I talked about it already. Okay, the next perfect number is 28. Duh. Right? Because what are its proper divisors? 1 times 28, 2 times 14, 4 times 7, but we don't count itself, right? These are the proper dividers. If I add these up, you get 28. That's why it comes up perfect. That's why these are perfect numbers. The next perfect number, of course, is 496. Does anyone want to take that on? Then there's 8,128, 33,550,336. How do I know? Right there, the perfect number eye chart is right over there behind the TV. You were in my summer school class, right? I showed you that. Okay, anyway, so some perfect numbers are odd. So that's even. They're all even. The first 5 are even anyway, so therefore false. How do you know for sure? Can you just look at 5 cases and then just base it on that? No. So how did you guys figure out how did you get the answer there? That's what I want to know. Just look at the bottom and copy it down. Okay, no, let's see if that works on the test then. So how did you verify that the statement was false? What did you do? Yoshina. And it just happened to be the answer on the bottom. Okay, no, we'll go with that. Okay, that sounds good for the test. Let everybody do that. Did anybody like look it up?
I have a question.
Yeah.
Could you just do the all statement instead and then the opposite?
Say that again.
Never mind.
What? No, what?
Like, if it's some perfect numbers are odd, could you check and see if all perfect numbers are even, and then look for the odd one?
All perfect numbers are even.
Never mind.
Well, I mean, yeah, exactly. So you can look at its negation and then determine if the negation is true or false, then by default, the original one is the opposite of that, right? You could do that.
Is there an easier way?
Yeah, just know. So if you don't know, what do you do? What do you do if you don't know something? Don't you find out? How do you find out? Look at that, it's on the bottom.
Ask Mr. Parker.
No, how about, did anybody look up perfect numbers on the internet? And then what? Oh, there we go, and what? What did we find out? Yeah, because why would I put something that's wrong? Yeah, so if you don't know, you looked on the internet? Yeah.
Why is number 9 the answer? Question mark.
Aha! Finally somebody's asking good questions. Do you guys ever wonder what's that question mark? That means we don't know. Okay, what you're referring to is the Goldbach conjecture. This is a very famous problem in mathematics. The Goldbach conjecture, named after the mathematician Christian Goldbach. Okay, anyway, what does it say? Every even number greater than 2 is equal to the sum of 2 prime numbers, right? That's the Goldbach conjecture now. You guys know the difference between like a conjecture and a theorem? A postulate? What's a postulate, first of all? Like in geometry, did you guys learn postulates? A postulate is a statement that's so obvious it doesn't need to be proven. You don't need to prove it, it's just too obvious. A theorem is a statement that needs to be proven. Is a conjecture a theorem? No, it's just a conjecture. Somebody just like conjectured it. You know what I'm talking about? They thought it up, but they don't know if it's true or not. Until somebody proves it's true or disproves it, we don't know. Anyway, so every even number greater than 2 is equal to the sum of 2 primes. So let's try. 4 is equal to what? This is what somebody came in and said. Oh, 1 plus 3. No, 1 is not a prime number. Go to your room right now. 2 is the smallest prime number. So what? What is 4? 2 plus 2. Okay, 6. Is that equal to the sum of 2 prime numbers? Yeah, 3 plus 3. What about 8? 3 plus 5. 10. 5 plus 5, or if you want to go 3 plus 7, whatever. Oh, it works for the first 4, therefore true for all. No. How can we actually prove this? Can you? What if you're in a Turkish prison and the only way you can get out is so you gotta prove this? What would you do? You just write down all the even numbers? You can't because there's infinitely many. How would you even prove something like this? Well, anyway, the last 100 years, maybe even 200 years, mathematicians have been trying to prove it, but nobody can. So right now, it's only a conjecture. We don't know if it's true or false. That's why there's a question mark there. Did anybody look it up on the internet? I'm looking over here for the 4 people that looked up the perfect numbers. Why not punch this in? Did you?
Yeah.
This. You punched it in. And what did it say?
It just showed me this table of like a triangle of all the prime numbers going down on each side, and then the sum of each one.
Did it mention the Goldbach conjecture?
Like,
And did it say anything about it?
said
There were too many words.
they checked until like 9 digits, but they still didn't find anything.
Yeah, see, so we don't know if it's true or false. That's why you have a question mark. Oh, so on the test, Mr. Park. So it could be true, false, or we don't know. So it's actually a 1 out of 3 chance. Yeah! Maybe. So somebody had a question? Question? It's a what? 40, 40, 40 chance? Okay, are you sure there's no questions? Because we're going to move on now. Oh. That's why you come across something in the homework. If you don't know, you just ask. Yeah.
How would you know what it is if you can't make it up during the test?
Sometimes you just got to take an educated guess. Sometimes that happens. Okay, anyway, today we got to learn how to make more truth tables. Okay, what are the 2 truth tables? 3 we learned yesterday: negation, or, and, right? We're going to learn 2 more. So you only have to memorize 5 truth tables, and then we're going to derive everything from that. Okay, so today the first one is the conditional statement. Okay, now this is the one you should have learned in geometry. Okay, let me give you an example of a conditional statement. Okay, I don't want to write it on, I'm just going to say it in words. If 2 parallel lines are cut by a 3rd line, then the alternate interior angles are congruent. When did we learn that? Yeah, and what subject were we studying in preschool? Geometry, right? Some of you learned it in 9th grade as well, yeah? If 2 parallel lines are cut by a 3rd line, then the alternate interior angles are congruent. Yes or no? You learned that before, right? See, a conditional statement has the form if P, comma, then Q. If 2 parallel lines are cut by a 3rd line, then the alternate interior angles are congruent. Most of the time, when you read theorems, theorems are stated as conditional statements. Right? If P, then Q. Okay, now, like I said, mathematicians, we don't like to write out the words, so we symbolize. Here's the symbol for it. Woo! Doesn't that kind of make sense? If P, then Q. See how the arrow's going from P to Q? So, if P, then Q. Okay, unfortunately for you, that's not the only way that you can state this. The most common way would be if P, then Q. But another common way would be P implies Q. This is all in your notes. Doesn't that kind of make sense? P implies Q. That's why the arrow goes from P to Q. Okay, but here are the ones you're not going to like. P only if Q. Q if P. P is a sufficient condition for Q. That's in your notes, so that's why I'm not going to write out the words. Q is a necessary condition for P. All of these things mean the same thing. If P, then Q. So do we have to know them all? No, you don't have to know any of them. It's just that you're going to have a hard time on half the test if you don't know it. Yes, you got to know it. That's why it's on the notes. But probably, I don't know what's going to happen. You just never know what's going to happen on a test. Most of the time, I just use this one and that one. Most of the time, I just give you the symbol, so it really doesn't matter. Yeah? But then once in a while, I like this one. I like them all. They're like all my children right there. I just like them all. Okay, now what does the truth? Oh, wait. Before we even get to the truth table, if you have a conditional statement, if P then Q, P implies Q, whatever, you can form these other statements, right? This is what you learned in geometry. You have a conditional statement. P implies Q. or if P then Q, we can form other statements. Okay, let's see if you guys remember. What is the no? Yeah, let's do that first. No, let's start with the converse. What is the converse of if P then Q? If Q then P. How do you know? From geometry, right? No, but come on. Okay, here's the conditional statement. What is the inverse of that statement? If not P, then not Q. And then the last one, okay, maybe this is the word you heard from geometry. The contrapositive. Does that word ring a bell? Contrapositive? So you're going, okay, well, it doesn't matter because I'm teaching you like you don't know anything, right? How do you form the contrapositive from a conditional statement? If there's only one other possibility here. If not Q, then not P. Do we have to know that? Yes, that's why we're covering it. Okay, so if you're given a conditional statement, you have to be able to form these other statements. Now tonight, you're going to be making truth tables. So now you know when you're making the truth tables, what are you looking for? You're looking for things that are like exactly the same, so that we can say they're logically equivalent. Don't just go through it and you're done. You gotta learn. Okay, now what does the truth table look like for the conditional statement? Now, when you have two statements P and Q, how many possibilities are there again? 4. So the standard way: true, true, false, false, true, false, true, false. Okay. Here is the conditional statement. Wow. Okay, now when is the conditional statement gonna be true? Well, here, to me, this is the easiest way to remember. The only time the conditional statement is false is when the first one is true and the second one is false. By the way, when you have a conditional statement, what do we call the first part? It's in the notes. In a conditional statement, the first part is called the hypothesis, the second part is called the conclusion. Okay? Anyway, the only time a conditional statement is false is when the first one is true and the second one is false. That's the only time it's false. Okay? It's true in every other case. Okay, to help you understand, okay, maybe you can think of this. What if I made the statement? If you do your homework, then I will pay you $5. If you do your homework, then I will pay you $5. Okay, so what happens if you do your homework and I pay you the $5? Am I a liar? You guys actually have to think about that? No, I'm not a liar. What if you did your homework and then I didn't pay you the $5? Am I a liar? Yes, I'm a liar. What if you didn't do your homework and then I paid you $5? Am I a liar? No, I'm just stupid, right? What if you didn't do your homework and I didn't pay you the $5? Am I a liar? No. So maybe if you think about it like that, it kind of makes sense, right? But to me, the simplest way to remember it is the only way a conditional statement is false is when the first one is true and the second one is false. All other cases true. Okay, any questions on the conditional statement? There's a lot. Okay. Now, when you do your homework tonight, things are going to get kicked up a notch. Now, when you notice things, well, we'll just see what happens tomorrow. See what kind of questions you have. Okay, the second and last truth table we have to know is called the biconditional statement. Okay, let me give you an example. A triangle is equilateral if and only if all 3 sides are congruent. Did you ever hear that phrase before? If and only if? That's called a biconditional statement. A triangle is equilateral if and only if all 3 sides are congruent. You know? So the way we symbolize that is this. Why don't I just write it out? P if and only if Q. This phrase right here is the biconditional. And the symbol we use, here. Notice the arrow goes both ways. Why? Why do you think? Because it's biconditional. See, a conditional, the arrow only goes one way, like this, right? P implies Q. if P then Q. But a biconditional can go either way. You can go if P then Q, but you can also go if Q then P. And that's why they call it the biconditional. So you can kind of see, oh, okay, so anyway, that's how it is. So what does the, oh man, look at that. What does the truth table, before we even do the truth table, where do we see biconditional statements? In fact, the example I gave you, a triangle is equilateral if and only if the three sides are congruent. Where have I seen that phrase before? Is that a theorem? No, it's a definition. Normally you see biconditional statements in a definition. Right, because think about it. If a triangle is equilateral, then the three sides are congruent. But if the three sides are congruent, then the triangle is equilateral, right? It can go either way, biconditional. Anyway, this is what the truth table looks like. PQ, so true, true, false, false, true, false, true, false, woo! And then the biconditional, P if and only if Q. This is it, true, false, false, true. Okay, now, if you want to figure out a way how it works, though, when is the biconditional statement true? Here and here. When both of the components are the same. So if both are the same, either both true or both false, then the biconditional is true. But if they're different, it's false. That's how you remember the biconditional. Okay, now based on these 5 truth tables, you have to derive everything. Okay, you got to look for logically equivalent statements and things like that. Okay, so let me give you an example. Can we remember this? Plus you have it in the notes. I'm going to erase. Okay, so tonight's homework, what kind of problems can you expect? Well, again, constructing truth tables. In fact, why don't I do one like I've never done before? Just so you guys understand. Okay, I will do this. Construct the truth table for not Q implies not P. Usually I have you guys just discover it on your own, but I'll do one for you. How do you make truth tables? Well, like I told you yesterday, if you need to make the training wheels on the side, put the training wheels on the side. Okay, here's the training wheels. What are the 4 possibilities? True, true, false, false, true, false, true, false. This does not change. That always stays the same. That's just standard. Okay. So if Q is true, false, what is not Q? False, true, false, true. And if P is true, true, false, false, not P is going to be false, false, true, true. Oh, we have a conditional statement. Okay, now, when is the only time a conditional statement is false? When the first one is true and the second one is false. So, false, false, what does that mean? It's true. True, false. False, true. True, true. There you go. So this represents, did you guys double box and make an asterisk? Because that's expected on the quiz. Okay, there we go. So just move on to the next problem. No! In fact, I'm doing one of your homework problems for you. Hey, I've seen this before. Where have I seen true, false, true, true? If P, then Q. So, do I have to do it again? Okay, I will. They're the same. So what did I just learn from this problem? P implies Q is logically equivalent to not Q implies not P. I'm going to box that. In fact, if you look at your notes, it's in there. So what did we just learn? Any conditional statement is logically equivalent to its contrapositive. This is one of the most, I'll tell you right now, this is one of the most important things in this whole chapter right there. If you just have to pick the 10 most or 5 most important things, that's on the list right there. So any conditional statement is logically equivalent to its contrapositive. They mean the same thing. Now, you know, I told you some applications of logic. Remember the bullet train in Japan? You know what another application of logic is? Law. Any of you thinking of becoming lawyers? I bet some of you are. Okay, anyway, if you want to become a lawyer, you have to take this test called the LSAT. You guys have heard of that? You heard of that regular SAT? Well, they got the LSAT. And if you want to do well on that LSAT, you know what you need to know? Logic. So many of my students have come back to Mr. Park. Thank you for teaching us logic, because since I remembered the contrapositive and stuff like that, the law test was easy. Because if you think about it, law is you have to be able to think logically, right? No, I can think like a crazy man. Oh my goodness. Okay, anyway, so that's the kind of thing you have to discover when you do tonight's homework. Okay, look for things that are logically equivalent. Okay, you guys know how to do truth table. Okay, one other thing, last thing for today. Are there other applications of logic? You bet your bippy there is. Because remember, in the logic that we're studying, every statement is either true or false. There's only two states. Can you think of some everyday application that only has two states? Like, okay, I'll give you a hint. On and off. On and off. Electricity. Okay, here's a wire. Either your current is flowing through it or it's not, right? How many of you are in physics this year? Okay, so you guys are going to learn about electricity and stuff like that. Anyway, here's a wire. Either current's flowing or it's not. You guys know what we call when the current is flowing? Okay, you ever heard of this thing called a computer? It has, how do you turn the computer on? Okay, maybe that's a bad question. Because you guys just have that button, yeah? But usually you have an on-off switch like this. On, off. Do you guys notice that sometimes it doesn't say on and off? Sometimes it has 1 and 0? Electronic devices, you guys ever notice that? That's because 1 means current is flowing. 0 means it's not. 1 is on, 0 is off. So yes, we can apply logic to electrical engineering. Okay? So if you have a wire, if current is flowing, 1, you can think of that as true, and 0 is like false, off. Okay, so now what we're going to do is we're going to build electrical networks now. Okay? So suppose you have a wire, and then this is standard electrical engineering, okay, symbols right there. This symbol is for, if you look at your notes, this is the symbol for not. It works exactly how not works. So if you have a wire coming into this, we call this a gate. This is a gate, a not gate, okay? So it works exactly like that. It negates. So if you have current coming in, or whatever, okay, a wire coming in, and the state is on, 1, and it hits this, what do you think the output's going to be? 0, because it negates it. It changes it. If it's 0 coming in, what do you think the output's going to be? 1, because it negates it. It changes it. Negate means it oppositizes it. Is that a real word? Okay, now suppose you have 2 wires coming in. Okay, you got this. This is like the Star Trek symbol. What's Star Trek? Okay. Well, if you look at your notes, this is OR. Okay, this is standard electrical engineering. It works just like the OR statement. Okay, so let's say if this is 1 and this is 0, it hits this gate, boom, it has an output. What do you think the output's going to be? Okay, now remember, 1 is true, 0 is false. How does the OR statement work? The OR statement is true when at least one of them is true. Is at least one of them true? Yes, so then it's true. And then of course, if there's OR, there's AND. Okay, this is what the AND looks like. You got these 2 wires coming in, and AND looks like this, right? It goes like that. AND. Okay? So if this is 1 and this is 0, what's the output going to be? It's going to be 0, because how does the AND statement work? It's only true when both of them are true, but if one is true and one is false, it's false. So these are the 3 standard electrical engineering symbols you use, and then you just derive everything from it. Okay, let me give you an example. Okay, suppose you have 2 inputs coming in. P, Q, okay, then. And then E, jump over. You guys know how to jump over? You guys seen that before? And then this one gets negated, and then and then these 2 go together, and then and then these 2 go together, and then and then negate, So you're gonna have something like this in your homework. Okay, so this is what like an electrical engineering diagram looks like. Okay. Okay. First of all, symbolize this. How would you symbolize this? Okay, what's the first thing that happened? Okay, this is what? Which one is this? Or, okay, what statements get ORed together? P and Q gets negated, so P and not Q. Right? Okay? Then this gets ANDed, that's AND, right? With what? What is this? Where did this come from? P, so P gets negated, not P. But then the whole thing gets negated, so wong, yeah. And there you go, that's how you symbolize it. Doesn't it? It just makes sense, right? Okay, and then the next question you're going to have on your homework is going to say something like this. If P was 0 and Q was 1 in this network, what is the output going to be? Well, one way is you can look at the network, or you can just look at this statement, right? Because they're both the same thing. This is just a representation of that, right? So in other words, if P is false and Q is true, what is this statement right here going to be? So which one you want to do? You want to look at the network, or you want to look at the symbolization? Look at the network, okay? Okay, if P is false and Q is true, so Q gets negated, what? So now it's 0. So you got 2 zeros going into OR, 2 falses with OR. It comes out 0. Now, if you're smart, you don't even have to look at this one, right? Because the only way the AND statement is true is when they're both true. So if one of them is false, it's going to come out false already. It really doesn't matter what this is, right? You know what I'm talking about? Okay, and then if this is false and then it gets negated, what's the output? Right there. So the output is 1. 50-50 chance. That's right, it's either 1 or 0. Oh, so is that why we have the binary number system? That's why electrical engineering's got to know the binary number system? Yes! Because it's just a strings of 1s and 0s, like this, 1, 1. You guys ever heard of the binary number system? So if you're going to do computer programming, electrical engineering, you got to know the binary number system. Basically, it's just ons and offs. That's all it is. You guys even know how? Okay, I'm afraid to ask this, but do you guys know how the binary number system works? Like if I gave you this number, what number does that mean in base 10? You guys are, you know why humans do base 10? Because we have 10 fingers. That's how they counted in the old days. Although somebody still probably uses fingers. Okay. But the binary number system is for computers, because computers is just electricity, right? On and off. That's why you have the binary number system. Okay, now how do you convert this into a number we can understand, base 10? Well, first of all, you got to understand base 10. Okay, for example, okay, give me a number. 4,352. You guys understand what that means, right? What does that, okay, go back to elementary school. What does that mean? 4,000s, 300s, 5 10s, and 2 2s, right? Is that how, the way they taught you, right, in elementary school? Yeah, so what is this? This is the ones place. This is the tens place. This is the hundreds place. This is the thousands place. Now do you see why we call it base 10? See, they're all powers of 10. Okay? This binary number system is simply base 2. There's only 2 digits. See, in the base 10 system, there are 10 digits. Right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? In the binary number system, there's only 2 digits, 0 and 1. Okay? So what place is this? This is the 2 to the 0 place, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6. Right? Okay, so what is 2 to the 6? 64. So that means we have 164. So there's 164, no 32s, 116, no 8s, no 4s. I got 1 2 and 1 1. So if I add them up, 83. So that number represents 83 in the base 10 number system. See, but you guys are just so used to this, right? 2 1s, 5 10s, 3 hundreds, and 4 thousands. It's the same thing. And you can make any other base. Like, okay, since we have time. What if you have, okay, let's do the same number, 4 3 5 2, except this is base 7. You put it over there. What if you're working in base 7? Who would work in base 7? I don't know. So what does that mean? This is the 7 to the 0's place, the 7 to the 1's place, the 7 to the 2's place, and the 7 to the 3's place. Okay, so that means I have 4 7 to the 3rd powers. What is 7 to the third part? Quick, what? 49 times 3, come on. 49 times 7. Quick! Hanaoka! Thank you. So you have 4 343s. So what's 343 times 4? Quick! 2 carry 1, carry 1. 1372. Okay, and then you have 3 49s. What's 3 times 49? 7 carry 2, 147. And then I have 5 7s. Now when you can do it, what is 5 7s? Are you serious? 35. And then I got 2 1s. 2. So if you add them up, what is that? 6 carry 1, 5 carry 1. So this number in base 7 is equal to 1,556 in base 10. Then somewhere in elementary school you have to have learned different bases. Somewhere. Okay, to end today. So if you're going to do computers, if you're going to major in some kind of engineering or some kind of computers, you got to know the binary number system, and you also got to know the hexadecimal system. What's that? That's base 16. Hexadecimal. That means base 16, there's 16 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, but what do we do after 9? Yeah. A, B, C, D, E, F. There you go. So you can probably guess A means 10, 11, 12, 13, 14. Oh, so now you can see what's on the test, yeah? In the hexadecimal system, make up a word. Ace. Ace 32 in base 16. What number is that equal to in base 10? Wow. How come usually we get like 10 minutes at the end. And then we just, oh my goodness. We have to go back to elementary school so many times. We have to fix that.